All right, so kind of from here on out, we're going to be digging into processes in much greater detail. So we're going to start with Overland Flow, which is the basic, kind of the basic part of the GSSHA model. So Overland Flow is represented as sheet flow in the model. So if you're in a grid cell, the water is a uniform depth flowing across that cell. And so you can think of like what it looks like when you get a big thunderstorm that runs across a parking lot. It's just perfectly uniform, centimeter deep flow running across the parking lot, getting your shoes wet. It does, interact with small scale topography, and you can kind of represent that. Things like on the right, which maybe, it's not exactly flat. And there are some areas that are trap water and stuff. You can put in a thing called a retention depth, and that'll hold an amount of water until the water gets up above it, and then the water flows out of it. So we talked about the generation mechanisms. Seems like a long time ago now, but there they are. Plus a couple extras didn't really talk about it because they're kind of like out of the norm. Storm surge is a way you can get overland flow, and then out of bank stream flow. When the stream comes out of its banks and flows over into the overland flow plain and creates additional stream flow. And so in our model, that we get overland flow versus runoff transformation. So I don't remember the point of this slide. There, do you?
Yeah, where we can have spatial differences.
Yeah, so I mean, it's kind of comparing the lumped models with the physics-based models, and so we're computing actual hydraulic flow as opposed to transformation of rainfall to runoff. That's the gray box. It's kind of showing like it's that's like if you put some feature in the overland flow based model, you're going to, where you put it matters. But if you just have a transformation model, it doesn't really matter because it all works off of percentages. It's the same percentage of the basin. So if you're just looking at percentages of land use type thing, then where it is doesn't really matter. But if you put it in hydraulics model, change that land use, then it's going to make a big difference, right? And so where you put it's going to matter. So our overland flow scheme in GSSHA, we have a mesh of 2D grids, grid cells, and as Aaron mentioned, we use a 4-point flow scheme. So we compute flows. It's actually a finite volume method. So in finite volumes, you compute across faces. Our grids are squares, so our faces are like that, and our computations are like that. And that can lead to those pits that we were seeing in our model setup. These are the actual equations that we're solving. We're solving the continuity equation. And if you put the continuity equation that's at the top in the finite difference form, it looks like the second line there. And the definitions are shown there in the bottom right corner. So you get fluxes across those faces. And then the H is the depth. So the Q's are unit fluxes, and the H is the depth, and T is the time. So you look at the change in the depth over time. It's kind of what we're computing there. The calculation of flow. The shallow water equations are listed up there at the top. That's the full St. Ferdinand equations. What's kind of helpful is to think about it in terms of what the different terms represent. So the first term, change in flow with respect to time, that's an acceleration term. That second term, the change with respect to space, so q squared over h is the advection term. That's the term that makes the shallow water wave equation so hard to solve because it's highly nonlinear. The next term is a pressure term, and then the last term is a friction term. So if the pressure term is large compared to the other terms, then you can reduce the equation to a very simple form. And that is the diffusive wave equation. And the diffusive wave equation is proved very useful in many circumstances. And so the diffusive wave equation is what we solve inside of GSSHA. And so to solve it, it breaks down to where it looks like that, and it's solved in 2 dimensions. So you have the same equation in 2 directions. And so what it's saying is that the change in the head, and that's the elevation plus the water depth, is equal to the slope of the water surface minus the friction slope, and the friction slope is the water surface slope. So we solve that. So that's the equation in 2 dimensions, the same in the y, looks the same. And that's the finite difference form at points 1 and 2. So you get it would look like that. And then to get the q's, back here somewhere, we get our q's by using the Manny's equation. And the Manny's equation is written for normal flow. And so if you look up the Manny's equation, it's going to have the surface slope, the land surface slope at SO over here. But to make a diffusive wave, you substitute the friction slope, which is the land or the water surface slope, or is that here? And so that gets you your flows. So that's the set of equations that you need to solve something. And so, like I said, it's a finite volume, and the method is a forward weighted, and it's dependent on flow direction. So you always solve from upstream to downstream, and flow directions can shift during time and space. And so you're always checking to make sure you're solving from upstream to downstream. And there's 3 different methods that you can use. The explicit method was the original method. If you don't really use it anymore, it's fast, but it's not very accurate. The ADE is kind of I guess the basic one that we use now, and I think it's the default that you get. And so it has a nice feature, and it has a time variable solution, so it will cut the time step down to keep the model stable, and then it'll speed it back up to keep the model fast. And the way it does it is computes the flows in one direction, then it updates the depths, and then it computes the flows in the other directions, and then it updates the depths, and it switches that out every pass. There's another one, ADEPC, which has a prediction correction step, and it corrects its errors basically as it goes. It's extremely stable, but it's slow, and so basically don't use it unless you can get the ADE to run. Scheme properties, yeah.
Yeah, it's pretty like finite difference, finite volume. Can you explain how you could you start with the finite difference?
Well, when you look at when you write it out, there's no difference in how a finite difference in the finite volume. If you write it out like that, there's no difference in how it looks. And so in a finite volume, you have a control volume, and you solve based on that control volume. And a finite difference, you're basically solving across a grid, a grid of points. And so it's not necessary, the advantage of finite volume is it's mass conserving. Finite difference is not necessarily mass conserving, but when you write the equations out in finite difference form and finite volume form, it's the same. But it's the solution, how we solve it, what makes it finite volume. That makes
So it is a finite volume.
it is finite volume, but that is finite, it says in finite difference form, but you could write finite volume form right up underneath there. It's the form of the equations, how you solve the equations makes it finite difference versus finite volume. So the solution is a finite volume solution, even though I say that's a finite difference representation of the equations. And it is, but it's also finite volume.
You switch from differentials to differences.
Yeah,
That's that. So,
yeah. Our solution is finite volume because we're solving fluxes and we're
So you're solving it.
we go way back. I don't know how far back I have to go to find the picture. I mean, so we're solving this here. So that's a control volume. And then we're solving fluxes across the control volume and then updating the value within the control volume based on the fluxes. And that's not what you would do if you were to solve this finite difference. You don't worry about the volumes in the finite difference. You would solve for the heads, and you can end up with mass balance problems if you just solve for the heads. And you don't know. It doesn't necessarily the fluxes in the head don't necessarily line up in finite difference. They should, but they don't necessarily have to. So we solve everything above the ground finite volume. We solve everything below the ground finite difference. Because it's slow underground, and you don't tend to get any volumetric errors based on using finite difference for the below ground slope process.
So when you went to the finite volume, was that what helped you go to larger computational time steps? It seemed like, when we were doing.
These better schemes. It was always finite volume. The explicit scheme was it's a bad scheme, really. It's not a good scheme. The ADE scheme is much better, and the time variable solution lets you get with a bigger time step, and it'll keep itself stable.
Right.
Originally, before we came up with the time variable solution, the ADE EPC was the best solution because it's stable, it's second order accurate, and these both are.
I know at one time we had a bad problem with negative depths.
That was using the explicit scheme.
Right.
Yeah. But they're much better. They're much better now, and it's very stable. The advantage of solving a diffusive wave as opposed to a full dynamic wave equation is it's a lot more forgiving. So it doesn't require a continuous median. You can't solve dynamic wave across water that's not there. And so when you have a dynamic wave solution and you have wetting and drying, then you have to play shenanigans almost to avoid that wet dry issue. And diffusive waves naturally doesn't cause a problem. It also avoids shocks that you find in dynamic wave, which is the full dynamic wave equation. And the simpler form of the equation is the kinematic wave equation, which throws out the friction slope and only uses the slope of the land. But that actually is a shock-inducing formulation. So it causes problems even though it's simpler in form. Diffusive wave smooths transitions in flow. So it's forgiving there. It does, but it still captures backwater effects. That's where the water's backing up due to the downstream, water surface being higher than the upstream. And you can use it to bring in outside boundary condition like a tidal surge. So if I have a high water on the edge of my boundary, higher than what's inside, then it's going to flow into my boundary. So it gives you that ability to bring that in. So the basic formulation has some issues, and that we know managed roughness is not constant with depth, and that's the way it's written and solved in there. We know diffusive wave can smear surface water profiles near transition. So if you were to look at a solution with GSSHA in the string versus say RAS, the lines would pretty much follow top of each other, except for where things are changing rapidly. And in those cases, the full dynamic wave equation is going to capture that transition accurately, and GSSHA would smooth it out. Diffuse wave smooths that out. So that's where we know it's inaccurate, because it doesn't solve that part of the equation. The other probably more problematic thing, especially for hydrology, is that, because the flow has no momentum and flow directions can change due to very small changes in water surface. This can be a problem. You can start kind of sloshing, and especially if the water surface is very flat, and then there's a tiny little change and it goes one way and it overflows, and then it gets a tiny little change and it starts to just kind of wiggle. If you get these wiggly water surfaces, or worse, you can get going, if it gets out of control, it can start to go dry or even negative.
Does that happen when there's
Typically, no. It's usually a problem where it's very flat.
when it's flat?
When it's very flat, because you think about it, it is almost completely flat water surface, and maybe there's over here it's a millimeter higher than here, and then it flows over here and brings it up 2 millimeters. Well, now it's higher over here, and it flows here. And so normally it'll just sit there and wiggle, but it can start to, then it goes negative and it crashes. So that's an issue with diffuse wave. The biggest problem with it, I would say. So based on some of these things, we did some things to try to solve them. And so we introduced a depth varying managed roughness. We added an inertial formulation for the discharge, and then looked at, not that this was a problem, it was just kind of a special feature. You have floods in urban areas, you get blockage of the flow due to the buildings. You have to flow around the buildings, you can't flow through the buildings, obviously. So the depth varying managed roughness. So resistance to the flow, especially the roughness, varies with the depth as the water varies. So we know the overland flow roughness values are about an order of magnitude greater than channel roughness parameters. And where a problem comes, so you think about hydrology, you think about flows on the overland of millimeters to centimeters maybe. And that's water running off in a normal kind of fashion. But if you have floods, you might have a meter of water on the ground, say 2 meters, whatever. And so in that case, the roughness values that you put in for the overland flow, they're not really effective anymore, because a meter of water sees sand a lot differently than a millimeter. And a millimeter of water flows around sand like it's a boulder. A meter of water runs over it, picks it up, and washes it away with it and doesn't feel it. And so our calibrated roughness values are going to be way too high. Like I said, like by an order of magnitude. So for the model, if you want to make the model robust to work in all these different depths, then you have to vary that managed roughness. And so, if you think about it, in most hydraulic problems, you don't have this issue because you're not switching from one extreme to another. But in hydrology, we're always pushing, we're always trying to do too many things simultaneously. And so there are many forms of depth varying managed roughness. I thought the exponential form was the best, and that's basically where you take the initial value, and that's the one that really represents overland flow in a true sense, that sheet flow. And then you vary it exponentially based on the depth, and then a parameter. And those parameter values are typically, they have to be between 1 and 0 and a value of about 0.5. It's a typical value you find in the literature. Although the literature is poor on this, I must say, it's not like a lot that's been done. And is this good? It's probably adequate, is what I would say. And it does seem to help when you have this issue. Another thing we can do is we go back to our shallow water wave equations. There's our full form up there at the top. Yeah, there's gonna be a test question on this one next slide. As I mentioned before, we don't like infection, so we still want to stay away from infection. But we can rewrite that equation. There's a lot of math to be done to get from A to B down there, but I've done it and it does work out. And that expresses our flow, and then that flow, as opposed to just the flow based on the Mann equation, that flow has a momentum built into it. And so it does a magical thing. It kind of gets rid of that problem where you have the little oscillations, because it's not purely based on the depth of water anymore. It now includes the momentum of the water flowing. So it's going to tend to keep it flowing in the direction that it's going. It's going to have some persistence. And it provides more stability in flooded conditions.
So solving those the explicit equations, so you need like a solver, like PEC or something.
No, it's explicit. It's explicit, not implicit. Yeah.
So that means you do not need like one of those fancy solvers.
No, we don't make a big matrix to solve it. That's an implicit solution. We do that for the subsurface. We're not going to talk about subsurface solutions in this class, but so we do. No, so this is all explicit, and in general, you solve hydraulics problems explicitly. It just lends itself to it.
What is the S factor?
What's that?
What's the S factor in the middle equation at the very end on top?
That's a friction slope. That's still friction slope. That hasn't changed definition. So basically what we've done is in our diffusive way, we cut out the whole middle, and now we're keeping that friction term. We threw that friction term out. Now we're keeping it, and now we have a more complete formulation. The last thing is just a flow blockage, where we look at, you can put in a map of where the buildings are basically, and then you can create change the flow patterns based on the buildings. They're going to block the flow, and that'll give you a more realistic flow pattern through an urban area, and give you kind of the right flow depths and stuff.
Does that get used on the New Orleans model?
No, this is all after that. All this stuff, all of this. Oh, somebody made a new picture. Yes. So wetlands are a special overland flow cell. And the thing about them is they have 3 types of flow. And there's, so you think about a wetland, and it's got vegetation, some emergent vegetation, and then some layer of gook or peat or something down at the bottom that the water can actually flow through. And so, when we compute the flow in a wetland cell, you define the vegetation, you define the peak depth, and then you get three types of flow. You get a turbulent flow above the vegetation, which would be solved the equations we were just talking about. And you get a Darcy flux through the vegetation, and a Darcy flux just like you would get through the groundwater. And then a Darcy flux through the peat layer. So you get these three different flow patterns. So it has a complex flow pattern. And in my experience, that if there's significant parts of the watershed that are in this, that are in what is best defined as a wetland, then this three layers of flow captures dynamics that just trying to solve the Overland flow equations won't capture. Even if you really jack up the retention depth, because I have in the past run models where we captured wetlands with a high retention depth. And sometimes that works, but sometimes that does not work. We're going to add some wetlands and define these parameters. So you'll kind of understand better, I think, when you do it yourself. Basic model requirements. So to do the overland flow, we need certain things. We need a land surface elevation. Of course, that comes from our DEM. I think we said that enough times. Our managed roughness and retention depth, and the retention depth is accounting for microtopography. That comes from our land use. Of course, there's our rainfall input. We have different methods. Have an outlet location and slope. That comes from our DEM. And then a cell size and a time step, a model time step, a controlling time step, that's defined by the user. So that's just a couple of considerations about these sorts of things. So the grid is the basis of your model. As we talked about earlier this morning, so the grid cell is our computational element. So information at the grid cell level, actually below the grid cell level, is lost. That's not worried quite right. So things to consider is, what is the resolution of your input data? Don't ever make the grid size smaller than the resolution of your DEM. That's just disastrous. So then think about, what features am I trying to capture? Am I in a huge, agricultural area where the fields are miles long, or I'm in downtown New York City? It's going to make a difference. So what's the purpose of my model? Am I trying to capture something very fine, or trying to capture something very coarse? So that's going to affect how much how big of cells do I want to use. And then what are the dominant processes? So you want to try to capture your dominant processes. You want to keep slopes in, you don't want to lose slopes. You don't want to you can get too coarse and loose slopes, and that's something to think about. So the other thing you got to think about is your computational burden. So you need your model to run in a manner that's going to let you do your project on time. And another thing to consider is, do I want to be able to use automated calibration methods? And the answer to that is yes. And so I don't want the model to run so slow that I can't utilize those. And so it's a combination of watershed size and computing power. And at the current level of computing power, I think models with 100,000 to 1 million cells are of the right order of magnitude. I can remember when 1,000 cells was the right order of magnitude. So, things increase rapidly. But at this point in time, I'd say almost all of our models fall in that range. And then they run in timely manner and allow us to do automatic calibration. So, you think about the cell size requirements, and the computational requirements, and you have different size watersheds, so it's at 100 acres, you get, you can put in 10,000 cells, 10 meter cells, and you only have 4,000 cells, right? That runs at a blink of an eye. At 100 square miles, that 10 meters thing is getting a little bit large. You're up to 2.5 million, so that's probably too many. You're probably better off to down at 50. And you can see if you go up to 1,000 square mile watershed, like about the size of the Kishwaukee watershed Aaron talked about earlier, that'd be 26 million cells. So that's really too many. You could drop down to 50 and you're still at a million. Something like 100 meters or 200 meters is much more reasonable for that one. So you have to consider the important features. This is almost the flip side. So, you have these, think about it as the resolution goes, if you lose resolution, then, how things are defined. So if you look at that right-hand side, that's very fine resolution. And if you think about those being polygons on there, the grid and the polygon are going to basically be the same. If you coarsen it, you start to change shape, and at some point, it becomes like a cartoon of it. And so, is that good enough on the left? Well, you have to decide when you build these models. Only you can decide, right? That's something to think about. And and this is a picture from a study I did, and was looking at. I can't remember what the study was, but it was looking, trying to decide on my grid size, and there on the left, there's a 100-meter grid, and you see you can see the polygons up there, and the cells, the different colors, and so you can see the representations of things, and it just depends on what you're trying to capture. So, I'd say you look at those blue things were these lakes you were wanting to really capture. They're pretty cartoonish there at 100 meters, but over at 50 meters, they really are pretty well defined. And so if that was what I was concerned about, then I might want to say, well, 50 meters is better. But if I was concerned about those bigger areas and just kind of capturing them, well, then 100 meters is totally fine. So it really kind of depends on what you want to do, right? It's not like I can say there's a right size. The right size is what captures the features you're interested in capturing. Time step selection. For using the ADE method with the variable time step, then it doesn't matter so much anymore, but this kind of thing is still semi-important. There's a relationship in doing numerical modeling where you don't want what's called the grid velocity. You don't want the flow velocity to exceed the grid velocity. And that means that a parcel of water will move through a grid cell without being captured. So it should move from cell to cell to cell to cell. It shouldn't move from the left to the right in one time step. Then your solution explodes. And so that's called the Courant stability criteria. And so for stability, you have to satisfy the Courant criteria. For accuracy and efficiency, the time step should be maximized. Time step is best determined with a convergence study. That means you try different time steps until you get a solution that's both stable and accurate. And that's over on the left, that little picture is showing a time convergence study. It shows where the model becomes unstable at 210 seconds. And then, at 180 has some wiggles, and then, maybe about 150 seconds is where it's a kind of ideal solution. And so you'll start to see things go on when your model is, time steps too large, the model crashes. That's obviously bad. The oscillations in the hydrograph, like we see over there on the left, checkerboarding, which I was talking about, that kind of cells going dry, that kind of sloshing back and forth. It looks like that. If you put out a map of the depth grid on that picture in the middle. Then the other thing, a little more subtle, is you look at the model computes with mass balances of itself, and then the mass balance error should be very small. If you're getting big mass balance errors, it's telling you that something's going wrong.
Does this have anything to do with it changing from diffusive to kinematic or?
No, that's just that's a diffusive wave. The diffusive wave, the inertial formula was meant to help with that checkerboarding when you have substantial depths of flow in the ocean.
So basically, when you do all diffusive flow and you're just minimizing the time step until there's no oscillation.
Basically, yeah. So, and then I think this is our last slide. How do you make this thing?
Is it safe to say most of our models lately have been running 10, 20-second time steps? Is that a good starting point, you think, Chuck, still, or?
I mean, it's a place to start, I guess. But I mean, I always want to run time. I always want to run time and space conversion studies, always, 100% of the time. Because you say you can save so much time down the road if you do it in the beginning. You kind of optimize your model for accuracy and efficiency in the beginning. This is a model that was put together a long time ago to just to kind of this demonstration. Yeah, it's a storm surge at Charleston, and this kind of gives you an idea of, I mean, it's really just kind of to show the overland flow, but it turns out to be kind of an interesting model because Charleston's kind of high around the edges and low in the middle, and so when storm surge gets in, it gets trapped. It does just what happens up there. You can see it kind of gets stranded over there on the right-hand side, and that's what happens, and that does what happens in Charleston when the storm surge. Anyway, that's Overland Flow.